Okay, so where we left off on Tuesday is really the most important part of trigonometry. And that is looking at a right triangle and finding missing pieces to it. And we have a couple of different possibilities. I might give you a triangle like this and tell you that this side is 12 inches. This side down here, we're going to make 35 inches, and we'll label it angles A, B, and C. It's traditional to let angle C be the right angle. And then the sides are labeled by what angle they're across from. So this side over here would be side little a, this would be side little b, and this would be side little c. And now we can find the other pieces of that. We can find side little c, angle A, and angle B. So we have a triangle. We know 3 of the 6 pieces. Now, a triangle has 6 pieces, 3 sides and 3 angles. If we know 3 out of those 6, in most cases, we can find the other 3. The only case where we can't do it is if what we know is all 3 angles. But any other set of information, we can find everything else. So here, let's find angle or side C first here. We'll find this missing side. This is just a Pythagorean theorem problem. A squared plus B squared equals C squared. Now what I'm missing here, I am trying to find that hypotenuse, C. So this is literally adding up the 2 sides I missed. So I'm going to shorten this up to enter it in the calculator. I'm going to enter it as the square root of 35 squared plus 12 squared. Now, I would encourage you, if you've got your calculator handy, try to enter these on your own. Beat me to the answer even if you can. So we get 37 inches is the length for side C. Now that Pythagorean theorem, or a squared plus b squared equals c squared, we've done that enough. We're pretty comfortable. We're pretty confident in that result. But I'm still not, I'm going to try to avoid using that measurement for other calculations if I can. It's kind of the engineer in me. For 2 reasons. One is I did that calculation. Every calculation I do, no matter how simple it is a chance to make a mistake. So whenever possible, we try to take when we go to do a new calculation, we try to go back to original information that was given in the problem so that we take out that layer of a possibility of making a mistake. The second part of it is, as an engineer, if I use that 37 and it's wrong, it's my fault. If I use the information given, in this case the 12 or the 35, and that information's wrong, well then it's somebody else's fault, which I know that sounds kind of bad, but the moral of the story is try to use information that was given rather than using different layers and depths into the calculation whenever possible. So let's look at angle A. So angle A is down here. 37 is the hypotenuse, but I'm going to try not to use that. The 12 over here, according to angle A, would be the opposite side, and the 35 be the adjacent side. It is touching angle A. So the trig function that we have that uses opposite and adjacent is the tangent of an angle is the opposite divided by the adjacent. So we're going to put in here, we're looking for angle A. The opposite side is 12 over the adjacent side of 35. To solve that, we do an inverse tangent. So the inverse tangent will cancel out the tangent on the left side. Our angle equals the inverse tangent of 12 over 35. The second tangent, 12 divided by 35. A couple of you have calculators that work slightly different than that. If you're having issues with it, let me know and we'll help you figure out your keystrokes there. That comes out to 18.92 degrees. At this point, we could just subtract from 180, or even just from 90, actually, since we have a right angle. to find angle B. But I'm going to go ahead and do the trig calculation to find angle B so that we can double check by adding the angles together to see if we get the right total. So according to angle B here, 12 is now the adjacent side and 35 is the opposite side. So it's still tangent. The difference is, for angle B, the opposite side is the 35 and the adjacent is the 12. So that angle B is going to be the inverse tangent of 35 divided by 12. So you enter that in the calculator, you get 71.08 degrees. How we can double check these, since this is a 90-degree angle here, the right angle, the other two have to add up to 90 to give us that total of 180 degrees, and these two do add up to 90 degrees. I'll have you guys try one in your notes. This will be a slightly different case. Oh, let's do 9 inches here and 41 inches here. Angles A, B, and C, side little a, little b, and little c. I'm going to ask you to find side B, angle A, and angle B. I'll give you about a minute and a half, and then we'll go over those. Okay, so side B, this is still Pythagorean theorem, a squared plus b squared equals c squared. However, in this case, we have the hypotenuse. Come on, right, there we go. And one of the legs. So to find the other leg, we are going to be working backwards. So the short way of entering this would be the square root of 41 squared minus 9 squared. The subtraction is because we have the hypotenuse and working backwards to one of the legs. Second square root, 41 squared minus 9 squared gives us 40. So that is 40 inches. Now again, if you feel more comfortable doing it, you can always do a squared plus b squared equals c squared. And you could have filled in 9 squared plus b squared equals 41 squared and solve that equation. I'm just starting to use this now because we've used it enough. I feel comfortable taking some shortcuts with it just to shorten up that calculation. Find angle A. Here's our angle A. According to angle A, of course, we're given the hypotenuse. The 9-inch side that we're given would be the opposite side according to angle A. The trig function that uses opposite and hypotenuse is the sine. So we'll put in the information we're given there. It is angle A that we're looking for. The opposite side is 9. The hypotenuse is 41. So A is equal to the inverse sine of 9 over 41. Second sine, 9 divided by 41. 12.68 degrees. Find angle B, using this here. Of course, the 41 is still the hypotenuse. That doesn't change. But the 9 is now the adjacent side, if we're looking at angle B. For adjacent and hypotenuse, the trig function is the cosine. Cosine of an angle is the adjacent side over the hypotenuse. So we'll plug in, it's going to be cosine of B equals 9 over 41. So B is equal to the inverse cosine of 9 divided by 41, which gives us 77.32 degrees. Oops, wrong key. 77.32 degrees. And again, you can double check. Adding those two angles up, we get 90 degrees, which gives us our 180 degree total for the triangle. So both of those cases where we were given two sides, we needed to find the third side and then the missing angles. Our next case is going to be slightly different. Here I'm going to tell you that this, I'll label them A, B, and C again. Little a, little b, and little c. And I'm going to tell you that angle A is 23 degrees and that side B is 28 inches. So now we need to find angle B, side A, and side C. So now angle B, we could find angle B really simply right off the bat by simply subtracting. 90 degrees minus 23 degrees will give us 67 degrees for angle B. So pretty simple, straightforward, just angle sum of a triangle. Sides A and side C, if we're going to use angle A here because that's the angle we're given, even though we're pretty confident of angle B, we did calculate it and there is that chance of a mistake. So we're going to go back to angle A, the 23 degrees, because that was a given angle. Side B here, the 28, is the adjacent side, according to angle A. If I'm trying to find side A would be the opposite side. The trig function that uses opposite and adjacent is tangent. The tangent of theta equals the opposite side over the adjacent side. So here we're going to fill in, it's tangent of 23 degrees is our angle. The opposite side is side A. The adjacent side is our 28 inches. To solve this, we put the tangent over 1, and we will cross, multiply, and divide. So when we enter this, it is tangent of 23 degrees. We have to make sure we close that parentheses, times 28, and divided by 1. Now, realistically, we don't have to do the divided by 1 because it doesn't change anything. So we get 11.88. We'll go 11.885 there. Inches. That is side A. 11.885 inches. Now, before we move on, let's check to see if this makes sense. If this angle here had been 45 degrees, we would expect these two sides to be equal. Since it is less than 45, considerably less than 45 degrees, we would expect this opposite side to be smaller. Or we could also look at the idea that this is 67 degrees and 23 degrees. We expect, remember we said the largest side is opposite the largest angle, smallest side is opposite the smallest angle. We would expect this side, because it's across from 23 degrees, to be much smaller than this side, which is across from the 67 degrees. So it makes sense. So now let's go back and find side C. Again, I am going to stick with trig functions so that I can use the information I'm given. Well, side C is the hypotenuse, and I'm still going to use side B as the side I'm given. So the adjacent side and the hypotenuse, the function that uses that, is the cosine. Cosine of an angle equals the adjacent side divided by the hypotenuse. So I'm going to put in the angle is 23 degrees. The adjacent side is the 28 inches. And I'm trying to find the hypotenuse, the C. So I put the trig function over 1, and I'm going to cross, multiply, and divide. So it's 1 times 28 divided by the cosine of 23. So I don't need to do the times 1. 1 times 28 is just 28. Divided by the cosine of 23 degrees gives us 30.42 degrees. Not 30.42 degrees, this is inches, sorry. 30.4218 will go then. When we're going lengths, it is customary to go to 3 decimal places. When we're doing angles, it's customary to go to 2 decimal places. So that is 30.418 inches. So a couple things to double check here. This is the hypotenuse, and yes, it is the largest side. But the second thing to double check is the two legs still need to add up to be more than the hypotenuse. Well, 28 plus 11.8, that's 39.8. That's bigger than 30.418. So yes, the two legs do add up to be larger than the hypotenuse. If we ever get to that situation where the two legs add up to be smaller than the hypotenuse, well, then it just can't work. Because what's happening is if you have this leg here, let's say this is your hypotenuse, you have that leg and this leg. If they don't add up to be the size of the hypotenuse or bigger, they never reach each other. So it can't form a triangle. So when we're double checking, that's what we're checking for, is to make sure those two legs, when they're added together, are at least as large as the hypotenuse. I'll put one up here for you all to try in your notes again. I'm going to give you this angle down here is 58 degrees. Label my sides little a, little b, little c. And this time I am going to tell you that side C is 40 inches. We're going to ask you to find angle A, side A, and side B. We'll give you, again, about a minute and a half there, and then we'll go over that. Okay, so to find angle A, again, it is simple subtraction. 90 degrees minus angle B, which is 58 degrees, gives us 32 degrees for angle A. Side A is a little more difficult. So for finding side A here, we're going to be sticking with angle B, because that's what was given. I will label this as 32 degrees over here. We're given angle B, so we're going to stick to using that where possible. So angle A, or side A here would be the adjacent side, and of course the 40 inches is the hypotenuse. So adjacent and hypotenuse is the cosine. Cosine of an angle equals adjacent over hypotenuse. Now if you look it up, secant also uses adjacent and hypotenuse, but most of your calculators do not have a secant function, so we try not to use that. So we put in our information here. It's the cosine of 58 degrees equals A over 40. And we solve that by putting the cosine over 1, and we will cross, multiply, and divide. Cosine of 58, we make sure we close our parentheses, times 40 divided by 1. We get 21.197 inches. This is 21.197 inches. Side B. Using angle B, side B would be the opposite side, and of course we still have the hypotenuse. So that's going to be the sine. Sine of an angle equals the opposite side over the hypotenuse. Now again, I realize it gets a little redundant, but I do try to always write down the definition of my trig function first, so then I can substitute in the information I know, and it helps me make sure I get stuff in the right spot. So the angle is angle B, that's the 58 degrees. The opposite side is side B that I'm looking for, and the hypotenuse is the 40 inches. So I put this over 1, and now I'll cross multiply and divide again. So sine of 58 times 40 divided by 1. Again, I realize I don't have to enter the divided by 1, but I do just for form. Okay, 33.922 inches. Once again, we should check to make sure this makes sense. Angle B is larger than angle A, so it makes sense that this leg, B, is much larger than leg A. Also, this is like 34 plus 21, which is 55. That is bigger than the hypotenuse. The hypotenuse is still the longest side, but the two legs add up to be larger than the hypotenuse, which is, something we need to happen for this triangle to work. So let's look at some applications of this mess. One of the applications that's very common is to square up a foundation. And this really doesn't use the trig functions, but it uses trig. Most of us don't think of that Pythagorean theorem, a squared plus b squared equals c squared, as being trig, but it really is. So let's say I have a foundation that is 40 feet by 28 feet. And when I'm setting it up, I want to make sure it's squared. So I can find the corner-to-corner distance. That corner-to-corner distance will be our square root of 28 squared plus 40 squared. Giving us 48.82622. Now, obviously, we don't have a 48.826 whatever marking on our tape measure. So we're going to do some converting here. That is 48 feet. I'm going to remove the 48 to be left with the decimal feet. I have to turn that back into inches, so I'm going to multiply by 12, giving me 9.91. So that is 9 inches. I subtract the 9 whole inches, being left with the decimal, and I'm going to turn it into sixteenths. Setting up a foundation to the nearest 16th. Actually, for many people, the nearest 1/8 inch is close enough, but we're going to go to the 16th. Giving me 14.6, which is 15 sixteenths. So squaring that up, I would measure across there as 48 feet, 9 15/16 inches should be my corner to corner distance setting up that foundation. This one's more of a geometric application, but it can be thought of as a construction application if you look at dimensioning a city lot. So let's say you have a city lot where this is 210 feet there. This over here is 290 feet. And you're given that this angle between them is 71 degrees. And it is a parallelogram. You are told that these two sides are equal. Those two sides are equal. It's just not rectangular. The corners aren't 90 degrees. To find the area, we would need to know that height of that parallelogram. Find that height, we are looking at that triangle that I just drew in there that looks like that. So what we have is this angle here is 71 degrees. This hypotenuse is 210 feet, and I will label that, that is the hypotenuse. This side, the height would be right there, that would be this side. That is going to be our opposite side according to our 71 degree angle. So opposite hypotenuse, that is the sine of an angle, equals opposite over hypotenuse. And we'll substitute in our information. Sine of 71 degrees equals opposite side is our h over 210. And we'll make that a proportion and cross multiply and divide. So sine 71 times 210. And we don't have to divide by 1 because it's not going to change anything. That's 198.56. Well, 559 will go. 198.559 feet. So our area would be 290-foot base times 198.559 foot height across here. Again, notice I'm going to leave that in my calculator. I'm just going to multiply by the 290 to get an area of 57,582.08 square feet. Well, the question comes up, well, is that a big lot? Well, take a look. Depending on the city, in some of your smaller cities, the average city lot is between 1/2 and 3/4 of an acre. In some of your larger cities, a city lot is like 1/4 of an acre. Here, I'm going to put that over 1. Convert this into acres. Put square feet on bottom and acres on top. 1 acre is 43,560 square feet. So the square feet cancel out. This is going to end up being divided by 43,560. Giving us 1.322 acres. So if that's a city lot, that's actually a pretty healthy sized lot at almost 1 1/3 acres. Another common application with job site setup, and kind of a surveying application as well. Let's say we have a hill. And we want to measure 2 things. We want to know what is the horizontal distance, and then what is the change in elevation between those 2 spots. One spot at the bottom of the hill and one spot at the top of the hill. Why is this important? Well, when we are surveying, land and distance is measured on a horizontal, on a flat surface. So a piece of land that's hilly and a piece of land that's flat, 100 yards is 100 yards no matter how much surface area there is. The 100 yards is measured horizontal. So there's much more surface area to this land because it's going up and down. This one goes straight across from the shortest distance between 2 points is a straight line. So that's going to give us less surface area, but 100 yards is still 100 yards. It's measured at that horizontal. So we need to know this length to figure out really how far it is between those 2 points. But what we're measuring with our surveyor's wheel, and this is approximately a flat surface, is we're going to measure that distance across there, which ends up being the hypotenuse of a triangle. The horizontal and the vertical always form a right angle with each other. Let's say we measure that distance, and it comes out to be 462 feet. So I want to know this horizontal distance and this vertical elevation from there. So how do I set that up? Well, what I do is there's an instrument called a theodolist. Sometimes even referred to as a theodolite. Very similar to a transit scope, but a transit scope can only go level and measure elevations. A theodolist actually can tilt up and down. So you would set that up here. It actually has a circle that basically is marked out as a protractor so you can tilt it. Then you would set up your sighting post down here. That has to be exactly the same height as the theodolist itself so that you're measuring parallel to the ground. And you tilt your theodolist until you are sighting exactly into that spot. And that'll tell you what this angle is. That angle here would actually be called an angle of depression because we are looking downhill. If we're at the bottom of the hill looking up, it would be called an angle of elevation because we're looking uphill. Angle of depression and angle of elevation really are measuring exactly the same thing. It's just depending on whether you're measuring it from the top looking down or from the bottom looking up. So let's say that we measure that angle and it comes out to be 17.3 degrees. I can now find those missing pieces because the 462 here is the hypotenuse. The x would be the adjacent side. So let's do that. That is going to be cosine of an angle is the adjacent and the hypotenuse. So this is cosine of 17.3 degrees equals x over 462 feet. That over 1, and we will cross, multiply, and divide. Cosine 17.3 times 462 gives us 441.10. Let's find y. Y would be the opposite side according to our 17.3 degree angle. So that opposite hypotenuse makes the sine of an angle. So we put this over 1, and we are going to cross, multiply, and divide. Well, we've got to put in our information, sorry. Got a little ahead of myself. Sine is 17.3 degrees equals the opposite side of y over the hypotenuse of 462. Now we can put that over 1 and cross, multiply, and divide. Sine of 17.3 degrees times 462 divided by 1 gives us 137.39 feet. That's 137.39 feet there. Now that is a huge drop in elevation. 17 degrees doesn't sound like a very big angle. But when we're looking at drops in elevation like that, 17 degrees is very steep. For road surveying, 8%, in fact, some federal roads, I think it's 6% that they use. But anyway, 8% is considered the maximum grade, maximum slope for most county and state roads. 8% would be 8 feet of rise for every 100 feet of run. So this angle here, call it angle A, the tangent of angle A would equal 8 over 100, which means angle A would be the inverse tangent of 8 divided by 100. When we divide that out, we get 4.57 degrees. That is about 4.5 or 4.6 degrees is the maximum angle of depression or elevation that we are allowed to have for most roadways when you survey out the route. That really isn't that much. It doesn't sound very, very steep, but it's considerable. On Highway 8 over by St. Croix Falls, I believe that's either a 7 or an 8% grade on Highway 8. That is a pretty steep downslope and down to the river there. Well, this Theodolus can be used for a lot of other applications as well. Last semester, we talked about cutting down a tree and having to figure out how tall it was, and we used the shadow and similar triangles to figure out the height of a tree. Well, we can also use a Theodolus. If I measure from the center of the tree over, let's say I come back here 200 feet. Then I set up my Theodolus, and I should be more careful how I draw that. And I sight from the Theodolus to the top of the tree. Now, first thing I have to consider is that Theodolus is not sitting on the ground. So let's say that Theodolus is sitting, we'll have it 6 feet off the ground. And I am trying to find the overall height of that tree. But what I'm going to end up finding here first is going to be this triangle here. This is still 200 feet, but this I'm going to call X because it's not quite the full height H. I'm very similar to our heel height when we added a heel height into our trusses. We had to find a different height and then add the heel height to it. So here we can find X because according to this, oops, I got to give you the angle here. So let's say we sight that and we get an angle here of 32.4 degrees. And so according to that angle, the 200 here is the adjacent side, and the X that we're looking for is the opposite side. So that is a tangent. Tangent of an angle is the opposite side over the adjacent side. So I'm going to put in my angle of 32.4 degrees. Opposite side is X, and the adjacent side is 200. And now we'll cross, multiply, and divide. The tangent to 32.4 times 200 divided by 1 is 126.92 feet. This is 126.92 feet. But we have to remember there's 6 feet here of height from the ground up to the level that our scope started at. So we add 6 to the 126. The overall height here is 132.92 feet of height. So, there is another major application of the Theodolist. When you get, for most of the residential job site setup we do around here, it's not tricky to get things lined up straight. Put it that way. Typically, around here, you're going to have a street, and next to that street, there's going to be a sidewalk, and that sidewalk is pretty close to being perfectly parallel to the street. So when you go to set up a house, if nothing else, you've got the sidewalk you can measure off of to get to the corners of the house, and then you can set up your house off of that. And that helps you make sure that your house is parallel to the street or straight to the street. And as long as other houses do the same thing, you might not be the exact same distance from the street, but your house should be lined up parallel sides to the other houses that are around it. Just because it's a more attractive aesthetic to have the buildings lined up like that. But if you're out in the country or out in the middle of nowhere, sometimes you don't have those references, or in certain areas they get really fancy with their road setup. They have, streets that, in order to slow down traffic, they have their streets wind back and forth or whatever. You don't necessarily have that straight shot to set up off of, measuring off of a straight sidewalk. So you need something to be able to line up your building so that the sides are parallel. So what we're going to actually look at here is, let's say that we have a house here, and we're going to build a garage off over here. I'm going to get in a little bit closer just to stay on the page. But we're going to build a garage over here. And we want these sides to line up perfectly, or as close to perfect as we can. So the way we can set that up is we can use this Theodolist again. And what we do is we can use some edge that we want to line up with. If it were on a city block, we could line up on the edge of a sidewalk. If we find a spot where the sidewalk is straight, we could line up on the edge of the sidewalk. Here, we would probably line up with the edge of the house. This is going to be our reference lines, that edge of the house. So I would set my Theodolist up so that when I sight down my Theodolist here, I'm sighting perfectly down the edge of the house. And then from there, I'll turn my Theodolist I'll leave it set there. I'll turn my Theodolist over to this garage that we're going to build, and I will locate where I want the first corner of that garage to be. And that corner is going to be off of this reference line, which is just an extension of that edge of the house, and the distance to the Theodolist. So let's say I set my Theodolist there. The Theodolist not only can measure angles up and down, but if you look at it from the top, when the scope swivels, there's a scale on here also that tells you how many degrees it swiveled from a resting position. So let's say our first corner of our garage, this angle is given at 41 degrees, and the distance over there is 52 feet. And that's where we set our stake for the first corner of the garage. Our garage, we want it to be 40 feet by 28 feet. We need to locate the other corners of that garage now based off of this information that we measured. Well, the first thing I'm going to do is I'm going to convert that into horizontal and vertical. So X and Y here. So I'm going to call this corner A, B, C, and D. Corner A, I'm going to erase this so I get a little more room here. Corner A was at 41 degrees. Do this. It's 52 feet at 41 degrees is the way we would write it. the x and the y coordinates. Well, x here is going to be cosine of 41 degrees equals x over 52. So I cross multiply and divide there to get x is cosine 41 times 52 is 39.24 feet. I is going to be sine of 41 degrees equals y over 52. Again, put that over 1, I'll cross multiply and divide. Sine of 41 times 52 gives us 34.12 feet. So this is 34.12 feet. This here is 39.24 feet. Well, for corner B over here, there's going to be a new triangle. That new triangle is going to look like this. That new triangle is going to have dimensions. This is still going to be just 34.12 feet. That's the same as dimension y here. This dimension is going to be the 39.24 plus 40. So that ends up being 79.24 feet. So to identify corner B, we need a distance. This distance is simply going to be the square root of 79.24 squared plus 34.12 squared. Square root 79.24 squared plus 34.12 squared. Close our parentheses, we get 86.27 feet. At this angle here, well, the tangent to that angle would be 34.12 over 79.24. So the angle is going to be an inverse tangent. Second tangent, 34.12 divided by 79.24, giving me 23.30 degrees. Now that makes sense. This was 41 degrees here. This angle here is going to be a lot smaller because it's stretched out further. Next, we would find the angle side C here, like that. Now for this one, we need to add on to both sides. This is still going to be the 79.24, same as what it was up here. Over here, it's going to be the 34.12 plus the 28-foot width of the garage. This will be 62.12 feet. So for corner C, this distance, once again, is going to be the square root of 79.24 squared plus 62.12 squared. That's 100.69 feet. 100.69 feet at all this. Oops, come on now. There. Okay. So then, for this angle, this is the opposite and the adjacent side. That's going to be tangent. So the angle is actually going to be the inverse tangent of 62.12 over 79.24. Second tangent, 62.12 divided by 79.24. Oops, I hit the wrong key. I did second tangent. The second didn't register for me. There we go. There we go, 38.09 degrees. That's 100.69 feet at 38.09 degrees. And finally, corner D. That's going to be this triangle right here. That triangle. This is going to be back to the 39.24 feet here. This is going to be that 62.12. And so this length here is the square root of 39.24 squared plus 62.12 squared. Well, 73.48 feet at, well, this angle here again is going to be an inverse tangent of the opposite, 62.12, over the adjacent, 39.24. Now, the opposite side is longer than the adjacent side, so we're expecting this angle to be more than 45 degrees. Giving us 57.72 degrees. So, when we go to set this job site up, as long as we have that theodolus in the exact same position, we can just turn it and get the 41 degree angle, measure out 41 feet. There's our first corner stake. Twist it over to 23.3 degrees, measure out 86.27 feet. There's our next corner stake. And right around our foundation, we can mark our corners, and we can go from there. Now, I realize this is a little bit of an intense example. We will do another example of this again after spring break, because I realize you guys have 9 days off, and just like me, in 9 days, a lot can leak back out of your head, so we will go over this again. With that in mind, rather than load you up with a whole lot more that you might forget over spring break, let's give you guys some homework and get you guys out of here. In the big book, page 859 through 860, exercise 34-3, and page 863 through 864, exercise 34-4. Take a look at those in the applications. Now, we're at a point here where you do need to do some of this homework in order to be able to understand the test, because the calculations are no longer the difficult part. When it comes to applications, it is figuring out where the right triangle is, or what right triangle we are working with, that is the difficult part. We had to draw those right triangles in here because they weren't really a natural part of the drawing. So make sure you are doing at least a handful of these problems so that you get used to picking those right triangles out. Okay, with that, we have about 20 minutes left. I will give you that time to get started on your homework. I'll be on the network here if you have any questions. Otherwise, you all enjoy your